Why are stars and planets spherical? Why do all large celestial bodies take a spherical shape? Are there any large celestial bodies that are not spherical? Celestial objects can take even bizarre and irregular shapes as long as they are small enough. However, there is a limit, dedicated by mass, beyond which every object tends to the spherical shape. Above this limit, in fact, the force of gravity overcomes the cohesive force of the larger surface structures, and any significant prominence is drawn towards the center of gravity with enough force to destroy it. As the mass increases, and with it the surface force of gravity, the shape of the celestial body therefore tends to be more and more spherical. Of course, there will always be small disuniformities because the sphere is a geometric abstraction. But is that really all there is to it? Let's find out together. How many planets are there in the universe? A lot. It is estimated about 1 sextillion. Do you know how much an octillion is? Quite a lot. A number so large, a billion trillion, that it is possible to make a mental picture of it. Try looking at it this way. Just to get an idea, the planet Earth weighs about an octillion times more than a walnut. Yet all this infinity is made up of objects that have one thing in common. They are all spherical. There is not one single cuboid, dodecahedral, or heart-shaped one to say. But why? First of all, it should be noted that we are talking about planets, not celestial objects. The word celestial bodies includes, in general, a myriad of objects with different characteristics and with shape that for various reasons can also be very different from the spherical one. Consider just as an example our galaxy, the Milky Way, which within a so-called halo, consisting of stars distributed in a more or less spherical shape, possesses a disc-shaped structure rich in gas and stars. On the other hand, if by celestial body we denote individual objects such as stars or planets, it is correct to say that the predominant shape is approximately spherical. The reason is also quite intuitive. The most massive planetary objects, be they stars or planets, are formed under the action of gravitational force, which is the force that leads the elements of matter to be attracted to each other, and then to the center of the growing body. And if myriads of particles are attracted to a common point of aggregation, in the end they can only lead to a spherical agglomeration. And the larger the mass that is being composed and the lower its density, the more the final result will be similar to that of a perfect sphere. The physical principle involved is similar to that which makes soap bubbles spherical, or fat bubbles in broth circular. Nature always chooses the shape that minimizes the energy involved. In fact, for the same volume, the sphere is solid with the least surface area. For this reason, the soap bubble tends to assume a perfectly spherical shape. In fact, tries to organize itself into the shape that uses the least amount of energy to sustain itself. Leaving soap bubbles and returning to planets, we can say that very intense gravity prevents any surface roughness from exceeding a certain height. For example, it can be shown that mountains higher than about 10 kilometers cannot exist on Earth because they would slowly sink in on themselves to a smaller size. Therefore, the Earth, with its mass, could never have a rougher shape than it has, except for the short time needed to level out the irregularity. On neutron stars, stars whose very high mass and density make the surface gravity 100 billion times more intense than what we experience on Earth, it is estimated that the highest surface roughness cannot exceed half a centimeter in height. Relating the dimensions to the Earth's scale, it would be as if there could be no mountains on our planet higher than 5 meters. The level that keeps the shape of an object possessing the physical requirements to be called a planet almost strictly spherical is the so-called hydrostatic equilibrium, a condition that is achieved when within it the gravitational force that draws matter towards the center is offset by the thrust due to the compression of materials. The concept of hydrostatic equilibrium also makes it possible to determine whether a celestial object is a planet, a dwarf planet, or a minor object such as an asteroid, comet, etc. In fact, let's not forget that according to the new definitions released in 2006 by the International Astronomical Union for our solar system, planets and dwarf planets must mandatorily have a spherical shape and have reached hydrostatic equilibrium to be declared as such. Hang on a sec, guys, before we continue. Be sure to join the Insane Curiosity channel. Click on the bell. You will help us to make products of even higher quality. But how massive does an object have to be to achieve hydrostatic equilibrium? It depends on what it is made of, basically the density of its upper layers. The fact is that gravity is actually a surprisingly weak force. An object has to be really big before it can exert a gravitational pull strong enough to overcome the resistance of the material it is made of. This, incidentally, is why you need not fear that your bodies will collapse into a spherical shape at any moment. Anyway, let's try to put some order into it. Although there are many factors involved in determining the shape of an object, in the end there are only 3 types that frame the problem. Objects around 400 kilometers in diameter. If such an object has a snowball density, that is about 1 gram per cubic centimeter, then it will be able to achieve a spherical shape. Mimas, for example, with a diameter of 396 kilometers, is the 7th satellite of Saturn and the 21st in the solar system in size. And it is the smallest celestial body known to have a spherical shape, thanks to a very low density, 1.15 grams per cubic centimeter. This example illustrates an important distinction: the difference between being spherical and being in hydrostatic equilibrium. The impact that created the huge crater that makes it resemble the Black Death left a scar that Mimas's gravity cannot erase. Sphericity alone, therefore, is not a sufficient condition to make you a planet. There must also be the achievement of hydrostatic equilibrium. Objects of the same size but with higher density will show more or less irregular shapes, such as Pallas and Vesta, for example, the 2 large asteroids in the main belt, which, although they have diameters even greater than 500 kilometers, because of their very high density, shape far from spherical. Objects with diameters around 1,000 kilometers. This size usually ensures a spherical shape but does not guarantee hydrostatic equilibrium. If the object is dense and is affected by a major distortion event, such as an impact, its gravity will probably fail to close the wound, and its overall shape will suffer. Remarkably, the largest body known to be not in hydrostatic equilibrium is Saturn's bizarre moon Iapetus, with a diameter of as much as 1,470 kilometers. Despite its low density, which should make it easier to achieve a spherical shape, its silhouette is in fact defaced along the equator by an unbroken mountain range. Unbroken and very mysterious, since its origin cannot be explained. On the other hand, do you know what the smallest spherical object in the solar system is in hydrostatic equilibrium? It is the largest asteroid, namely the dwarf planet Ceres, which has a diameter of 940 kilometers. Other spherical objects of this size in the hydrostatic equilibrium appear to be trans-Neptunian objects: Orcus, 916 kilometers, Salacia, 846 kilometers, Quaoar, 1120 kilometers, Gong-Gong, 1230 kilometers, and Sedna, 995 kilometers. Objects around 1500 kilometers in diameter. Objects approaching or exceeding this size, except Iapetus, all turn out to be perfectly round and balanced. In this category fall all the large moons of Jupiter and Saturn, certainly Titania and Oberon of Uranus, Neptune's moon Triton, Pluto, and Eris, and of course our own moon. In short, including the Sun, there are about 30 spherical objects, and also in compliance with the balance requirement. There are literally millions of small bodies more akin to flying mountains, with extraordinarily different shapes, lumps of boulders assembled in the most rambling of ways. As Comet Churyumov-Gerasimenko visited in 2015 by the Rosetta probe, or like the small asteroid Itokawa reached in 2005 by the Japanese probe Hayabusa. Not to mention objects whose shape eludes any attempt at classification, and I'm thinking of the incredibly ominous silhouette of the interstellar visitor Oumuamua, capable of stirring up endless theories about its origin as it traversed our solar system, or the inexplicable flying saucer shape of Pan, a tiny moon of Saturn nestled among its rings. All clear then. Practically is all the merit and demerit of gravity. But gravity is not everything. While gravity conspires to make planets spherical, the speed of their rotation simultaneously seeks to flatten them. The faster a celestial body rotates, the more disproportionate its equatorial bulge becomes. This is why there are no perfect spheres in our solar system, only oblate spheroids. Thus, Jupiter would be perfectly spherical if it did not rotate, but unfortunately it rotates quickly on itself in about 10 hours, and thus its equatorial diameter results 10% larger than its polar diameter. Likewise, Saturn, while Venus, which rotates very slowly around its axis in 243 days, is the most spherical planet of all. Even the Sun, due to its immense gravity and relatively slow rotation of speed of 25 days, can be considered a perfect sphere, but a significant percentage of stars in the sky rotate much faster and swell considerably at the equator. The case of Acrinar, the ninth brightest star in our sky, is emblematic. Its rotation period is 2 days, compared with about 27 for our Sun. To make matters worse, the star is much larger and more massive, producing an equatorial velocity of at least 250 kilometers per second, which is 125 times faster than the Sun. Faster than that, and the star would fall apart. This extreme speed generates an intense centrifugal force, which flattens the star, making its equatorial diameter, which is 11 times that of the Sun, 56% larger than the polar. In terms of flattened stars, however, it is in good company. Peculiar rotating stars are many, and among them we also find Regulus, Altair, and the very famous Vega. Red supergiants such as Betelgeuse and other stars of immense proportions may have a roughly spherical shape, but with considerable surface alterations due to their convective rise of hot gas that generates huge, irregularly shaped bubbles on their surfaces. And I want to end by mentioning galaxies again. They too in fact sport very varied shapes due to their rotation. If their global rotational motion were zero, they would take the shape of globes, as is the case with spheroidal elliptical galaxies, and as is normally the case with globular clusters. In short, there is never a dull moment in space. Don't you agree?